Watch this video in Lesson Reach. Pause and ask questions, take a quiz, or get help with assignments. Link below.
Have you ever, accidentally typed the wrong digit while entering your credit card online and the website? It just immediately tells you it's invalid. Before it even tries to charge the card.
Oh, yeah, that happens all the time. And today we're actually looking at the hidden looping math that makes that instant security possible.
Right. And since we're diving into some real mathematical logic today for this deep dive, I think I'll step into the role of the curious student. And, I'll let you take the podium as our lecturer.
I am totally ready to lecture. I mean, this is one of my favorite topics because it really bridges the gap between grade school arithmetic and modern cybersecurity.
Awesome. So we're pulling this from section 3.7 of chapter 3 from Contemporary Mathematics, and our mission for you, the listener, is to figure out how the incredibly basic act of telling time actually unlocks the secret behind that credit card security.
Right. So to understand that connection, we have to temporarily change how we think about counting.
Okay, how so?
Well, normally when we do arithmetic, numbers just stretch off infinitely in a straight line. But in clock arithmetic, the numbers cycle back on themselves. It basically revolves entirely around the number 12.
Oh, I see. So if it's 11 a.m. and someone says, I'll see you in 4 hours, I don't say I'll see them at 15 a.m. I just automatically know it's 3 p.m.
Exactly. You already do this naturally.
Yeah.
So section 3.7 formalizes this as modulo 12 arithmetic.
Modulo 12. Got it.
Right. And the textbook points out that if it is 3 o'clock, adding 14 hours or, 26 hours or 38 hours, they all land you at exactly 5 o'clock.
Wait, adding all of those totally different numbers gives you the exact same time.
Yeah. Because the mechanism making that happen is really just division and remainders.
Okay.
So if you divide 14, 26, or 38 by 12, they all leave a remainder of 2. You just add that remainder to your starting time of 3, and you get 5.
Okay, so if I'm picturing this visually, it's essentially taking a standard, infinite number line and wrapping it tightly around a circle so the numbers just stack on top of each other. 14 stacks on 2, 26 stacks on 2, and so on.
That is exactly the visual to keep in mind. The numbers just loop. But, you do have to be careful with the zero rule.
The zero rule.
Yeah, so if you calculate 12 modulo 12, the remainder is 0. But a traditional clock face doesn't actually have a 0.
Right, it just goes up to 12.
Exactly. So in this specific visual, a remainder of 0 just translates back to the 12.
Remainder of 0 equals 12. Got it. But a clock is just one type of loop, right?
Yeah.
How does this apply to other cycles? Because the textbook mentions a cat litter box example that seems perfectly mundane, but kind of proves the point.
Oh, yeah. Let's run through that one quickly. So imagine a 6-person family rotates emptying the litter box every 6 days.
Okay. A very specific chore schedule.
Right. And let's say you start on a Thursday.
Yeah.
What day of the week is your 10th turn?
Oh, okay. Let me logic this out. So 6 days per rotation times 10 turns, that is 60 days.
Correct.
But the week loops every 7 days, so we're operating in modulo 7.
Exactly. You're doing modulo 7 now.
So 60 divided by 7 is 8, which leaves a remainder of 4. So I take my starting day, which was Thursday, and add those 4 remainder days.
Yep. Keep going.
Thursday plus 4. So Friday, Saturday, Sunday, Monday, the 10th turn falls on a Monday.
Spot on. You're literally just finding the remainder of the cycle.
It really is an elegant shortcut. But, here is what I really want to unpack. How does this remainder math, whether it's for cat litter or clocks, actually protect our credit cards? You mentioned that instant security earlier.
Yeah, this is where modular arithmetic gets incredibly powerful. Every time you type a credit card number, the system has to ensure the number wasn't corrupted or mistyped.
Right, because humans constantly transpose numbers, like swapping a 6 and a 9.
Precisely. And to catch that, financial institutions use algorithms based on modular arithmetic. Your credit card number isn't just a random string of numbers.
It isn't.
No, that final digit is actually a check digit. It's literally the mathematical answer to an equation involving all the preceding numbers.
Wait, really? So the website isn't actually looking up my account instantly? It's just doing a math problem?
Exactly. It runs the digits you typed through a specific modulo formula. Often it's modulo 10. The system calculates a remainder based on what you typed.
Oh, wow.
And if that remainder matches the final check digit on your card, the system basically says, okay, valid number, and proceeds to contact your bank.
Okay, so if I accidentally typed a 9 instead of a 6.
Then the sum of the digits changes, right? Which
Yeah.
means the division by 10 changes and the remainder changes.
So it won't match.
Exactly. The newly calculated remainder will no longer match your final check digit. the math fails. The website instantly knows you made a typo without ever needing to communicate with a remote server.
That is brilliant. It's built-in offline error checking. Because the algorithm relies on the strict cyclical nature of modulo math, any deviation in the pattern immediately breaks the loop.
It does. It catches the error locally, which saves massive amounts of processing power and, prevents fraudulent or mistaken charges before they even begin.
Wow. So just wrapping this up, math doesn't always have to scale into infinity to be powerful. I mean, sometimes understanding how systems loop and cycle is the key to solving complex problems.
Definitely.
Whether it's scheduling household chores or silently securing millions of financial transactions a day, modular arithmetic is doing the heavy lifting.
The elegance really is in its universality, which, leaves you with an interesting question to ponder.
What's that?
Well, if these built-in modular cycles are the secret shield protecting our digital financial systems from simple human errors, what other hidden mathematical loops are quietly correcting our mistakes in everyday life?